Hello, everyone. We're back with the second in our series of screencasts on Chapter 7. We are working now with paired data. The packages you need today, in addition to the usual Tiger stats, you'll want the package ABD. So you'll want to run library ABD in RStudio. So we are studying as our parameter of interest in this section the mean of differences. And rather than define that in the abstract right away, I'm going to start you off with an example, and then we'll come to understand what the mean of differences is. So my example concerns Tadaran spiders, and you can follow this link here if you like in the slides to learn more about them. They're a very interesting genus of spiders. One interesting thing about them is that male spiders of this genus are much smaller than female spiders are. Here's a picture stolen from the internet of a Tadaran spider, and just generally the morphology of a spider in the first place. You think of them as having the 8 legs, 1, 2, 3, and 4 on one side, 1, 2, 3, and 4 on the other. But then there's also these 2 little feeler-looking things coming out of the front, and they're called pedipalps. Okay, and in a lot of spiders, they're kind of small, but in other spiders, they're quite big. They're almost like the size of one of their legs. And Tadaran spiders actually have fairly big pedipalps. And biologists wonder, why that is. Is there some particular adaptive advantage that large pedipalps have? Because it seems that large pedipalps might get in the way, of a spider, be kind of big and cumbersome. And so just this simple question of do the pedipalps get in the way of a spider? That requires some research right on its own, even before you approach the question of why do these big ungainly pedipalps stay around, genetically in the genus. So researchers wanted to figure out, do the pedipalps really slow these spiders down? And so they gathered 16 Tadaran spiders. You can think of them as a random sample from the population of all Tadaran spiders of size 16. And they took each spider and they timed the spider on a little sprint, across a couple of meters. I don't know how they got the spider to sprint. Did they drag some food along in front of it and have it chase the food? Or did they somehow scare the spider and get it to run? I don't know. But biologists are good at getting these things done in a lab, and they recorded the speed of the spider in centimeters per second. And then, rather cruelly, I'm afraid, they amputated one of the pedipalps from each of the spiders, okay? And then, presumably after the spider was given some time to recover from the trauma, they timed the spider again on that same sprint, recording his or her speed in centimeters per second. And then they calculated the difference in the speeds for each spider, the after speed minus the before speed. So like maybe after the amputation, the spider went, 2 meters a second. That's kind of fast. And before, it went 1 meter per second. And the difference, 2 minus 1, was what was calculated. Okay? So you really get one number for each spider, the difference in speeds. So what you've got here is paired data. Each spider was measured twice. We got this pair of measurements for each spider, but we're interested in the difference of the numbers in the pair. We're interested in the difference of the speeds. So let's say that after they took the measurements and they computed the differences, let's say they took the average of the differences, the little sample mean of the differences here, the 16 differences out of all the differences that could have existed if they could have somehow gotten all Tadarian spiders in the world into their study. The sample mean turned out to be 1.18 centimeters per second. And the standard deviation of those differences turned out to be 1.07. And there were 16 spiders. So that's a little summary of the results. And based on that summary, do you think we might have strong evidence here that amputation of a pedipalp increases a spider's speed on average? I mean, look at the sample mean. It's a positive number, 1.18 centimeters per second difference. So on average, the spiders in the study were getting a centimeter per second faster after they were amputated. Is that difference so big that it can't be just reasonably explained as chance variation in what spiders got into the sample, but is it really indicative of the fact that losing a pedipalp makes you faster, just generally for spiders out there? And so you can cast those questions into hypotheses if you're willing to define a parameter. So let's let mu be the mean difference in speed after amputation minus before amputation for all Tadarian spiders. So your population's all Tadarian spiders, but your population parameter is a mean of paired differences in the population. And that's what makes this section in the text special and different from the previous section. In the previous section, the mean was just, the mean of a bunch of numbers in the population. But here it's the mean of the differences of pairs of numbers in the population. And the null hypothesis just thinks that mu is 0. And so when you think mu is 0, then you think that out in the population, on average, amputating a pedipalp doesn't make any difference to the speed. Some spiders might get faster, some spiders might get slower, but on average, no difference in speed. That's what the null hypothesis is expressing here. And the alternative just disagrees with that. So how would you run the test? Well, because you still have a bunch of numbers from the population, these differences, you're still interested in one population mean, even though it's a mean of differences. So you can use ttestGC on this summary data. You say the sample mean is the 1.18, and you say the sample standard deviation is the 1.07, and you say the sample size, and you say what the null value is, and off you go. And so you get all that code out in the console, just like we're familiar with already from section 7.1. First of all is the descriptive results, which are no surprise to you now. You put them into the function. The sample mean of differences, the sample standard deviation of differences, and the fact that there were 16 spiders. And as far as the inferential results are concerned, your best guess at the mean of differences for all Tadarian spiders is your sample mean, the 1.186. But that could easily be off by a standard error or so. And the standard deviation of this sample mean is 0.26 centimeters per second. Next up in the output comes a 95 confidence interval for the mean of differences. And it runs from 0.6 centimeters per second to about 1.76 centimeters per second. Now notice that the null's belief of 0 lies entirely underneath that confidence interval. It's less than the least number in the confidence interval. So already things are looking pretty bad for the null hypothesis. It's not in the range of values that the data would consider to be reasonable for what that mean of differences could be. And when you come to the test of significance with the null and the alternative laid out for you, you get another way of looking at it. The test statistic is that t-statistic we've been talking about. It's the same thing. And so what we learn here is that the sample mean of differences, that 1.186, was really like 4.4 standard errors above the value of 0 that the null is expecting it to be around. So this is very unusual. It looks, again, really bad for the null hypothesis. So again, I'm just reminding you, that the t-statistic, which is this difference that you observe between like the mean you got in the sample versus what the null is expecting it to be, it's called the observed difference. It's being divided by the standard error for x bar. And so it's computing how many standard errors the x bar is above or below what the null hypothesis expected to be. And that's why if you believe in the null, you're like really shocked by this test statistic value here, because the results are 4 standard errors above what you were expecting. So like if you ever had to compute the test statistic by hand, and that is a really sort of way outmoded way computers do this all for you now, then you could just use this formula and you could use the summary information, the sample mean that we had and the sample standard deviation we had and the sample size, and you could plug it into this little fraction here and get the test statistic by hand. But thank goodness R just computes it for you. But if you had to do it, I'm just saying, for some other course, if you ever had to do it, you could just use R like a calculator. The sample mean minus 0 is just the sample mean, 1.186. And then you divide by the sample standard deviation divided by the square root of 16. Make sure, though, that you put all of that in parentheses so that all of that is divided into the 1.186. And that's how you would get your 4.4. Now, the next thing up, and the very last thing in the output, is the p-value. And it's pretty small. It's 0.005. Well, 0.0005, 3 zeros. And so when you turn that into a percent, that's 0.05%. So remember what the null value means. It means here, if the null is right, if the null hypothesis is right, then there's only about a 0.05% chance of getting results at least as extreme as the ones we got in the study. So what do we decide about the null? Well, the p-value is so tiny. It's so unlikely to get this kind of stuff if the null is right. It's way, way tinier than our usual cutoff level of significance, 0.05. So we've got to reject the null hypothesis. We really have to conclude here that this study provides strong evidence for the alternative hypothesis, that Tadare spiders get faster on average after the amputation of a pedipalp. And so, the pedipalps do slow the spiders down. We're pretty sure about that now. So whatever it is that keeps those pedipalps around, in the genetics of Tadare spiders, I guess it's because they confer some other advantage on the spiders. Maybe they're useful for the spiders to, grab things to eat or to fight well or something like that. But they sure don't help them run fast. Now, All of this was just to illustrate to you how you could use summary data and stick it into ttestGC to do inference on a population mean of differences. But again, quite often, you're going to have access to the raw data, the original data that comes in as some kind of data table. And so, like, how would you do it if that was the case? It turns out that for this example, the original data is in a data frame that's provided by that package ABD. And the data frame is called spider speed. So to learn about it, you should maybe run view and help on spider speed over in RStudio. So I'm going to go and do that now. And so every row in the data frame is one of the 16 spiders. And the two variables measured are the speed of the spider in centimeters per second before amputation and the speed after. Okay. And so in the original data, the differences in speed are not computed for you. But that's okay. You can actually make ttestGC compute those differences for you. You just run ttestGC and you say twiddles, and that just tells R that some variables are coming up, and you do speed after, and then a minus sign, and then speed before, okay? And then, of course, you got to say what data set those variables live in. And you got to say what the null hypothesis thinks the mean of the paired differences is for that population out there, and the null thinks it's 0. And so if you were to run that code in RStudio, then you would get this output that we're going to go through bit by bit. The descriptive results would be provided first, and so it makes it pretty clear in this table that the average of the 16 differences, speed after minus speed before, is the 1.186, and the standard deviation of those differences is the 1, and then there were 16 spiders. And I should just sort of let you know that in some textbooks and some courses where you talk about this stuff later, the mean of the differences for a population is sometimes called mu sub d. D, to remind you, it's a mean of differences. Okay? And so, this right here is not the mu sub d. That's just our estimate of the mu sub d based on our sample. But it is our best guess at what mu sub d might be. But the standard error for that guess, that mean of differences, also called a d bar sometimes, is 0.2684. So we figure the real mu d is probably around 1.8, but give or take 0.264 or so. And we get that confidence interval again. And we get our test of significance again. And we get the p-value. And, it was 0.0005. Well, over here in the output, that shows up as 5 times 10 to the negative 4. 5 divided by 10 to the 4th power, the 10,000 there, the 0.0005. And so you could continue to make a decision against the null hypothesis. You can reject it. You could write your conclusion. But there are some advantages of having the original raw data that you don't get when you do summary data. And this is true anytime you're working in statistics. And one of the advantages is that you can go ahead and look back at the original sample and check it. You can actually do the check step in a test of hypothesis. And remember the check step here. If the population that you're picking from is not necessarily known to be normal, then you're hoping that either the population is pretty close to normal, or the sample size is pretty big, like maybe bigger than 30. And the sample size here is only 16. So it's really a good idea to check the sample to see if it's, maybe skewed. So one way you could do that in our code is you could use the function width. And you say with spider speed, take those variables inside it, the speed after and the speed before, and just subtract them. And that becomes this new variable called diff speed in your global environment. I'm just going to copy that, okay, and run it over here in RStudio. Those are the differences in the speeds for the 16 spiders. And then we could make a little density plot, remember GF density, with that variable diff speed. We don't have to say what data frame it lives in because it doesn't live in a data frame. It's just sitting there in a global environment. And we want to make it burly wood inside and make the boundary of the plot be maybe black. And let's go ahead and get a little rug of individual values, okay? Just like in chapter 1. And there it is in our plotting window. And here it is over in the slides. And so we can look at those 16 differences and we can see this distribution is kind of right skewed. The tail's going off to the right. So it's kind of right skewed. And that means, well, the sample is right skewed, then maybe the population is also kind of right skewed. And so kind of far away from normal. And the sample size is kind of small. So maybe this t distribution approximation for the t-test, it might not be all that reliable. Maybe we can't trust the p-value that we're getting from this routine to be the real p-value for this situation. And maybe the confidence, the 95% confidence interval, doesn't really have the level of confidence that it advertises itself to have. Here's another example. This is a very interesting one. Go ahead and run a view and help on labels. Labels is a data frame in the TigerStats package. And over here in help, you've got to go get the one that's in TigerStats. So we'll click on that. And what we learned by reading the help and then looking over here in the view is that this data set records the results of a kind of an interesting experiment that was actually performed at Georgetown College by a couple of students on 30 of their friends. What they wanted to do was to see whether people's perception of the quality of peanut butter was affected by the labeling on the peanut butter jar, as opposed to just how the peanut butter actually tastes. And so they set up this experiment where they had a room and they had a little table with a chair at it. And on the table were 2 jars of peanut butter. And one jar was labeled Jif, which is, the famous brand name that's heavily advertised, and it's kind of expensive. And the other jar was labeled Great Value, which is like the Walmart brand, and it's cheaper. And one by one, each of the 30 students that agreed to be part of the study was led into this room. And they were shown the 2 jars, and they were allowed to taste, like the spoonful from each jar was like scooped out for them, and they tasted each of the peanut butters. And they rated each peanut butter on a scale from 1 to 10, where 10 is great and 1 is lousy. And the students were told that this is just a taste test. We want to see which, peanut butter you like better. But what the students in the study did not know was that our two researcher students had actually filled both jars with great value peanut butter. So it was the same peanut butter in both jars, even though they were labeled differently. And so if a person's perception of quality is only influenced by the actual peanut butter itself, then they ought to give the same rating to both spoonfuls, you know? But look at what actually happened. Like, look at student number 1 in the study. They rated the Jif labeled peanut butter as an 8 and the great value as a 5. Student number 2 rated the Jif as a 10 and the great value as a 7. And you can go on through and just kind of look through these 30 students, and most of the time the student is rating the Jif peanut butter higher than they're rating the great value labeled peanut butter, even though it's the same peanut butter, you know. And so the research question that our two student researchers brought into the study is, will people rate peanut butter more highly on average if it comes with a Jif jar than if it comes in a great value jar? And so you can see again how this is paired data. Every row in that data frame was a student, but there were two measurements made on each student. How does the student rate the Jif labeled peanut butter? How does the student rate the great value labeled peanut butter? Two measurements, but they're paired because they're made on the same student. And so again, we're going to be interested in the mean of the differences in the ratings. So why don't we go ahead and let mu d be the mean difference in the rating, let's say Jif minus great value, for all Georgetown College students, if you could get them to all be in this study. And so the null hypothesis says mu d is 0. That's saying that even though one student may rate one higher than the other, the other way, on average, no difference. On average, label makes no difference. And the alternative hypothesis would disagree. And so we hit the code, and since the data come from a data set, then we just say twiddles the name of the first rating minus the name of the rating we're going to subtract off of it. And we got to say where those variables live, and we got to say what the null value is, and then off we go. Now, there are safety considerations. As always, we hope that our sample is like a simple random sample from the population. So we hope that. I kind of think that wasn't the case here. There were actually, there was a male and a female student that worked together on this, and I think the guy got friends from his fraternity, and the woman got friends from her sorority, and so it wasn't really like total random sampling from the Georgetown College population. And so I guess we're just fancifully pretending that it is here so we can work an example. Now the sample size is 30, which is like right at that cutoff for like big enough. So let's just go ahead and be cautious and check the sample to see if it's maybe too strongly skewed. And so again, you'll have to compute the differences. And so with the labels data set as your reference point, compute Jif rating inside of it minus the great value rating. And that's called diff rate, and just make a histogram of those differences. And when you look at those 30 differences, you can see it's unimodal and kind of left skewed, a little bit left skewed off in the left direction here. And so, there's some left skewness, or maybe you could call, those values here like outliers to the left. So that might be a problem if the sample size was smaller, but it wasn't. It was, it was fairly large. It was 30. So really we're okay here. You're always going to have to make those judgment calls when you're doing the check step on a test of hypothesis. And so don't stress out about it too much, Next up is the inferential work. The sample mean of differences is your best estimate for the mu d for the population. So our best guess is that mu d is about 2.367. But that guess could easily be off by 0.5 or so. Now, the null hypothesis expects the sample mean of differences to be around 0, give or take some for chance error. And what we actually got was like 4 of those standard errors above what the null was expecting. So it really does look bad at this point for the null hypothesis. And the confidence interval backs that up. The 95% confidence interval for mu d goes from 1.3 to 3.4 points difference. And so the null's value of 0 is like way, way down below the lower bound of this 95% confidence interval. Is nowhere near the range of values that could be considered as reasonable for mu d based on the data. So it's looking bad for the null. If you think of it in terms of the test of hypothesis, the test statistic is, this 4.6, standard error is above what the null is expecting. And if you head for the p-value, it's 7.42 times 10 to the negative 5, And, since the sample size is pretty good, we know from the math theory that if the null is true, then that test statistic has about a t-distribution with, 1 less than the sample size degrees of freedom. And so you can compute this p-value. R will compute it for you. And that p-value is like 7.42 times 10 to the minus 5 power, e minus 5 times 10 to the minus 5 power. And so just as a reminder of that scientific notation, 10 to the minus 5 is 1 over 10 to the 5, which is 100,000. And so 7.42 times 10 to the minus 5 is about 7 out of 100,000. And so when we interpret that p-value, we can say to ourselves, if the null is true, if the mu d is 0, if labels make no difference, then there's about a 7 in 100,000 chance of getting a test statistic that's at least as far from 0 as that 4.6 thing that we actually got. And so this looks, again, really bad for the null. The p-value is way less than 0.05, so we're going to reject the null hypothesis. And our conclusion is that this data provided really strong evidence for an alternative, that for Georgetown College students, the jar labels affect the perception of the quality of peanut butter. So there's a few examples where you can still use ttestGC that deals with one mean for one population, but it could be a mean of paired differences for the individuals in the population that you're wondering about. See you soon with another screencast, another section.